So today is, of course, the 31st. How comfortable are you doing graphical vectors? 0 to 5. 0, I don't know what a vector is. 5, I'd like to take my test now. I could do this in my sleep. 3, I get it right sometimes. I'm close. 1.98, okay. 3s, 4s, 2s, 4.5, okay. If there's one thing that you'd never master in this chapter, and it's graphical vector analysis, that's okay. It's a useful double check. It's like Fermi's. If you never really get the hang of Fermi's, it's okay. You'll survive. You'll do fine. You'll live a good life. They're helpful. They are helpful, but it's not the end of the world if it's the thing that you never quite get good at. You get that you're doing this and measuring the angle to find that direction between the resultant and the first vector. I think you get that. So now let's talk a little bit more about vectors conceptually. Kind of handy, you can move a vector parallel to itself. You may have discovered this at some point. So if I go 10 meters east, and then 10 meters north, and then 10 meters east, I can take this 10 meters east and move it up to there. Whoops, that didn't work. I can take this 10 meters north, and I can move it, as long as I'm moving it parallel to itself, I can move that to there. I can move that to there. Whoops. Yeah, that's as far as I can go. I will end up in the same place moving them parallel. You noticed this when you were doing your find a thing, find a vending machine, find a big bee, find an anything. As long as you move the vectors parallel to themselves, you can get away with this. So you can't move them off parallel. You got to keep them parallel. But the resultant will not change. You'll end up in the same spot. Actually, that doesn't work. You still got to keep heads to heads, tails to tails. There. That's better. You just can't read the words. You can add them in any order. I shuffled that deck of cards that you had. You followed them in an order that was not the order in which they were written. You found the object anyway. It doesn't matter if you go 10 meters north first or second or third. It doesn't matter if you go 10 meters east and then 10 meters east, or 10 meters east, then north, then east. It doesn't matter what order you put them in. It only matters that you follow each vector. Okay. Or in the case of your maps, you were able to cancel out some vectors. So you can add them in different orders. You can move them parallel to one another. That's convenient. You've kind of figured this out, and we talked about it a little bit. Not so much in terms of vectors, but we've talked about it in terms of things like velocity and acceleration. You can subtract them by simply adding their opposite, and you probably did this in your cards in the end. Oh, hey, we've got 10 meters east and 10 meters west. Why don't we cancel those two out? All you're doing is subtracting the 10 meters east from the 10 meters west. They cancel. So that's typically how we would add and subtract vectors. If you're using sign as a proxy for direction, you want to be really careful with this. And that's where visual representations of vectors are helpful. In that, be careful that you don't subtract a negative and end up adding those distances. You want to make sure that if your vectors are opposite, you're actually subtracting them, their magnitudes. Okay, and the last of these, when you multiply or divide a vector by a scalar, you still get a vector. So if we have velocity, which is in meters per second, which is a vector quantity, and we divide it by time, which is a scalar quantity, what do we get? Displacement, which is a vector quantity. So dividing by a scalar does not make it a scalar. Dividing a vector by a scalar, you still end up with a vector. We very often use this in problem solving. This is a nice algebraic trick. We'll start to use a lot of subscripts, and you got to get good at subscripts and get good at using really identifiable subscripts and subscripts that make sense. So velocity of the turtle is now v sub turtle. Velocity of u is v sub u. We're going to start to talk a lot about things like velocity on the x, velocity on the y, velocity initial on the x, velocity initial on the y, velocity final on the y, velocity final on the x, oy vey, acceleration on the x, acceleration on the y. And those subscripts are really important. A few of you who I noticed on the test want to use delta x for everything. Do not do it. We don't have a physics equivalent of a mole to beat you with, but I'm sure I can find something. You gotta use the designations for the axis you're on. That's going to become really critical because pretty soon we'll have velocities on the x and the y that will be different from one another. And you'll need to keep track of them both, and you'll have accelerations on the x and y that will be different from one another, and you'll have to keep track of them both. And your actual overall total velocity will be a resultant. And you'll be fine, I promise. This gets to that point. Use a coordinate system, stick to it. We do that whole superimpose the Cartesian coordinate system on the planet. X-axis along the ground works really well. Y-axis up into the sky and down into the earth works really well. That is what is pretty much universally used in physics, so it's a nice one to be familiar with. You could, you could show how non-traditional you are by making up something else, but I wouldn't advise it. Could you? Sure. You can make any coordinate system work if you're consistent, but the rest of the world is using x as the horizontal and y as the vertical. Now we're going to talk about getting the magnitude of a resultant algebraically. And Pythagoras is your friend. You all know Pythagoras. You're familiar with Pythagoras. A squared plus b squared equals c squared. You've been using it since what, 7th grade? 8th grade, probably? Beginning algebra, you've used it a lot. This works as long as you have a right angle. It only works if you have a right angle. Repeat after me. Pythagoras only works on right angles. Okay, you don't really have to repeat after me, I guess, because nobody's going to play along anyway. Why would you? I'm wearing a caftan. We're going to do that for magnitude of the resultant. So let's practice one just like that. So I'm doing just a made-up problem here. I'm doing displacements. I've gone 15.5 meters east, turned and gone 7.0 meters north. What I would like to know is my resultant. As always, the resultant connects the tail of the first vector and the head of the final vector. Okay, so what's my overall displacement? This is easy peasy. Note that I didn't write a squared plus b squared equals c squared, because this isn't generic geometry. This is actual physics, which is that math applied to the real world. So I'm writing this formula as the resultant is equal to square root of delta x squared plus delta y squared. That becomes important because next week you'll have delta x1 and delta x2 and delta x3 and delta y1 and delta y2 and delta y3 and delta x total and delta y total. So we want to make sure our labeling is good so that we keep these straight. All right, so fantastic. What's the resultant? Go. Okay, we've got a magnitude, 17.00735, blah, 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 blah. We only have 2 sig figs, so it is just 17, as the man with the fabulous hair stated. So we've got the magnitude. Now here's the problem. This is a resultant vector. It is a vector, which means what else do we have to have? Direction. So in this case, we have a right triangle, and we are interested in this angle right here. And there's only one way to get that angle. So 3 trig functions. I had signs up on the wall in the old building. I haven't gotten these. I need to get them laminated and hung again. But SOHCAHTOA, and the function that we're going to start off using is the tangent function. Tangent is equal to opposite over adjacent. So if we apply that to this, What we're actually going to use is the inverse tangent function. I'm going to set that aside. So if we want this angle, what we know is that the inverse tangent of this angle, or the inverse tangent, will equal theta. So the inverse tangent of the opposite over the adjacent, inverse tangent of 7.0 divided by 15.5. And if you're using the TI 30 multi-views, it's just second function tangent, gives you tan negative 1. I got 24.3045 blah 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 degrees is theta. What's my heading? So the heading is north of east because you are coming from the east and heading towards the north. It is 24, etc. degrees north of east. When you write a final answer for a problem like this, for your resultant, what you will write is that the resultant is 17 meters at 24 degrees north of east. Okay? Without a heading, it's half off automatically. You always have to show a heading for these. So I'm going to give you a couple assigned problems, and then while people are working, I'll look over tests with folks. Though I will say, and this is just sort of general words of wisdom on vector problems, so this is page 91, numbers 1 through 4. Though you don't have to solve these graphically, always draw a picture. It's going to come in handy with these because these are very visual kinds of problems. Visual learners tend to love these. I love these because you get to put everything in one place and sort of organize it visually. It's fantastic. Draw a picture anyway. It doesn't have to be to perfect scale, but it should be to reasonable scale or you will screw yourself up. That's it.